Alright, guys. Week 2 Physics CA. Which of the following materials are magnetic? This one is kind of just memorizing. It's iron oxide, powder, and cobalt. Guys, usually metals are magnetic. Carbon isn't even a metal, and aluminum and silver, you just gotta memorize that they're not magnetic. Okay. Which of the following statements describing magnetism are true? Permanent magnets retain their magnetic properties indefinitely. No, this is wrong. Permanent magnets can actually lose their magnetic properties by either heating, dropping it like mechanical shock, or running a current through it. Yeah. All ceramics are ferromagnetic. Ceramics are not ferromagnetic. Some metals are ferromagnetic, not all metals even. The magnetic properties of permanent magnets can be lost through strong heating. Yeah, wait. It's the same as this. I said that here, but let me explain why. Look, so you guys know a magnet. See, this is a magnet. Let's see, this side is the north, this side is the south. Okay? It has like tiny magnets basically inside it, like tiny magnetic particles there, I think. Or like something to do with the electrons, I'm not sure. But they're like aligned, okay? Let's say it goes all the way and it's the same right here. Okay, they're aligned in a certain way. They're all pointing in the same direction. Okay, that's what causes the magnetism in the magnet. Also, when you split a magnet, it becomes still like it's just two different magnets because they're still aligned. But heating, it causes the particles to move fast and move a lot, so they wouldn't be aligned. Running a current through it would also ruin the alignment. And when you drop it, when you keep dropping it or something like that, the mechanical shock, it also ruins the alignment of the little magnets, basically. So that causes the magnets to lose their magnetic properties. Okay? Magnetic forces are action at a distance forces. Yes, magnetic forces are interrelated with electric forces but not gravitational forces. Yes, they are. أصلا yeah. Which of the following are true about magnetic field lines? They never cross each other. If they were to cross each other, let's say you have two magnetic field lines, these two. Let's say this one, the vector of it is this way. The vector is tangent to the curve. You know how magnetic field lines are curved? So the vector is tangent to the curve. Let's say you have these two magnetic field lines crossing each other. They wouldn't cross each other. They'd just be one magnetic field line. Like it would be like this. And it's called superposition, I think. Yeah. It'd just be one line because this should be the add. When you add these two vectors, you get this line, and yeah. Ends at infinity, no, ends at the South Pole, goes from north to south. They are imaginary smooth lines. Yes, they are imaginary lines along which the magnetic field vector points at any point. Yes, yes. The term magnetic field describes the properties of the space around the magnet, the field around the magnet. If the plotting compass displaced at point A points rightwards, the direction of the magnetic field A is rightwards. Yeah, this is the same as the last option in the other question. Guys, like, what's it called? Let's say this is the magnetic field line. Let's say the vector at any point, let's say this point, it's gonna point like where the line is going. If it's here, let me draw with a different color so you can barely see. Here, it's gonna point where the line is going. It's tangent to the line. That's what they mean, yani, by the magnetic field vector points like where the line is. So here, in this question, the line would be like this. And like obviously, it's the same on both sides here, but I drew it bad. Okay, let me fix it wrong for you guys. It should be like this. And obviously it goes both sides and there's multiple lines and stuff like that. So yeah, that's what it looks. So see where the compass is, it's pointing towards with the like line. It goes from north to south. So this is north, it goes from north to south because the vector is pointing towards the thing. So this is south. Wait, let me explain fast. 5 minutes and 5 questions. The poles of a ring magnet are on its flat sides. Guys, a ring magnet is like a ring. Yeah. Nice explanation. Ring magnet is like a ring. Okay, so see? The flat side, so like the top flat side and the bottom flat side, one of them is the North Pole, one of them is the South Pole. You can imagine the ring magnet basically as a bar magnet that you curved in, like you made it into a ring. The poles are at the edge, like yeah. Same thing with the ring magnet. Poles of a horseshoe magnet are located at three ends. Yeah. Located at the three ends. Yeah, they're attracting, so opposites attract north, south. But no way they put positive and negative. Yeah, guys, this is what I mean. When you split a magnet, it's a bunch of small magnets. If you keep splitting it, it's gonna stay north, south, north, south, north. Like this is like this, north, south, and it goes on. If you split it at any point, it's just gonna be north, south. Because here, this side is south, this side is south. Like if yeah, if you split at any point, one side is gonna be north, one side is gonna be south. You can't have a magnet with one pole. Okay, guys, this is a bit confusing when I saw the question at first. I thought they were spinning it like this was going like this. They were spinning it in like a circle, but like no, they're not rotating the magnet like I thought. They're just holding it and moving it in this pattern. I don't know why they're doing this, but okay. I don't know why they don't just move back and forth. This is how that might thing is. Yeah, question. My God, I need to stop yapping. Okay, look. The north, it goes here, right? So when it's here at this edge before it goes up, this is what the magnet looks like. South, north. Wait, let me draw it clearer. Before the magnet goes up, when it's still touching the thing, this is what it looks like, right? South, here, north, here. South here, north here. And this, it's connected, right? Because they're stroking the steel bar, so they're touching. So then the magnets, it goes up. So they split the magnets. So this side is now what? South. And this side is now what? North still. So now this side is north. Now they keep repeating. So, you know, in the magnets, when ferromagnetics ferromagnetic materials are connected to a magnet, it basically becomes one big magnet. So now this is one big magnet. And then you split it because you took this magnet, you pulled it away. So now it's south, north, south, north. You're just like splitting a magnet. South, north, south. So the left side is north, north, and the right side is south, south. A small iron needle used to determine the direction of a magnetic field is called a plotting compass. Another way to say magnetic fields add as vectors is to say the magnetic fields obey the principle of superposition. Guys, this one, I think this one, there was two like this. And I said this one is going here and this one's going here. This one's going like this one's going like this. They're touching, they can't touch, so they just become one vector. That's what that is. The direction of a magnetic field at a point is the direction of the force it produces on a north pole placed on it. This is basically how the plotting compass works. The plotting compass is magnetic, so the north of the compass, it just points where the force is going. Okay, because it points to the south and the force goes from the north towards the south. The direction of the force on the compass by the magnet is directed. Okay, guys, this one Where do you think it's connect? Where do you think the compass is gonna point? Guess. I'll give you 5 seconds. Okay, that's too long. Okay. It, the magnet's like this. So at this point, it's going like this. Going like this. So yeah, that's what towards the right. Right. That's right. Rightward. Okay. Can I scroll? Okay. The net force by the magnet on the plotting compass is now, mm, guys, here it goes like this. See this? Because they're two opposites. They're not gonna like if this was south, it would go like this. It would just go from one magnet to the other. But this is not south, and the magnetic field lines cannot touch, so it goes like this. So perfectly in the center between them, the net force is zero because it's perfectly canceling out because it's perfectly in the middle. So here the net force is zero. Also, they want you to calculate the newtons. We have no, like, we still didn't learn any formulas to calculate the newtons from a compass, or like, I don't think we did, at least, like that. Yeah, perfectly in the middle, so zero. If a freely suspended magnet is placed at point 1, it will orient itself tangent to the field line. Yeah, it will orient itself like this. Tangent to the field line. The point 2 is the magnetic's south pole because it goes towards it. It goes from the north to the south. Oh. Yeah, see, guys, this is what I mean. They're not going towards each other, they're repelling each other. So that means the x is on north. Because this is north, so x is on north. Any plotting compass placed at the point labeled will retain its orientation at 3. Because there's no magnetic force, because they cancel out. Get it? The magnetic field is... Oh, guys, this... you can use iron to shunt a magnetic field or to shield it, basically. So now with the iron, the magnetic field isn't going to go back. It's going to go and it's going to be concentrated in the iron. So it's going to go and it's going to be concentrated in the iron. So basically, yeah, the iron is like taking the magnetic field. That's basically what it is. It's being shunted. Shunted. Okay. The strongest magnetic field is observed at the point labeled. Okay, guys, I do it. Yani you can tell which one's is the strongest one. Well, there's the most lines and where there's most concentrated. So that's 4. A sensitive compass needs to be protected from external magnetic fields. The best way to do so is to store the compass in a case made of soft iron. Yeah, because the soft iron, like, yeah, pretty much. I don't know why fully, but yeah, soft iron. North, so that's repulsion. South, north, so that's attraction. North, south, so that's also attraction. When a magnet attracts an object made of a ferromagnetic material, the latter behaves like a magnet. This phenomenon is called magnetic induction. That's the same as the one question. This one, I think. It's the one where you're rubbing the like, yeah, this one. This is a ferromagnetic material and this is a magnet. You're bringing them in contact and moving it and like bringing them in contact. That's also induction. This induction. The rods that can be magnetized by stroking them with a magnet. Also induction, it's the ferromagnetic materials, nickel and steel. The magnetic field, okay, let me draw it. It's going here. It's going here. It's going here. It's going this direction. Like this direction. And here it's going here. It's going here. It's going here. It's going this direction. So at A, it's going to the right because it's going out and then it curves. So at A, it's going to the right. At B, it's going to the left. At C, which is right here. Wait, is that C or is this C? This is D, right? It's D. Oh no, A is not right. Wait. This is not A, this is B. Wait. A is the one here. So A is going left. B is going right. My bad, I mixed them up. C is this one. It's going this way. So that's going left. D, it's going back into the magnet. Like it curved, indeed. It curved and it's going back into the magnet. So that's right. Right. Difficult to magnetize. Hard. Soft iron. Soft. Used in permanent magnets. Hard. Hard steel. Hard. Easy to magnetize but readily loses. Soft. Guys, soft basically gets magnetized easily, loses its magnetization easily. Hard is hard to magnetize and then stays magnetized for a long time. So permanent magnets, yeah, they're hard to get them magnetized, but then they stay magnetized for a long time. It's hard to get them demagnetized also. Okay guys, this question is a little tricky. I thought A would be 1 and A would have the strongest. When I solved it for the first time, I got it wrong. But A, actually guys, has the weakest. Because these two are repelling. Remember the questions where the point between them would have 0 newtons? It was somewhere here, I think. One of these few questions. Like around this area. So A is the weakest one. So it's 4. They want you to like order them from strongest being 1, weakest being 2. B, it's closest to the pole. It's closer to the pole than C. So B is stronger than C. So B is gonna be the strongest one. Wait, I meant to type 1. Wait. B is 1. Let's click. C is 2. And D is like far away, bro. Come on, that's not the strongest. Or not. 3, bro. Okay, 4, 1, 2, 3. A class of physical phenomenon in which matter exhibits interactions similar to those observed between magnets. It's known as magnetism, right? It's magnetism. Consider 2 identical rods, A and B. One of them is a magnet and the other is only a steel rod. The end of rod A is approached to the middle of rod B. Choose the correct answer to complete the following sentence. If rods A and B attract, then rod. Oh, okay, look. The end of A, okay, look. This is a rod and this is a rod. A is brought to the middle of B. So if they attract, what does that mean? Like this from the middle. That means that A is magnetic because A pulled B. Magnets, like in the middle here, they can't just attract something from their middle. Like the field isn't gonna they get attracted at the top. If it was gonna get pulled, it's gonna get pulled this way. But if they attract here, that means A is magnetic. Because that means A is the one pulling it here. If they attract. You get what I'm saying? If B was the magnetic one and A was not magnetic, then they wouldn't pull. Because it would be pulled towards the pole. Alright? So that means A is magnetic if they attract. The south pole of a plotting compass points east at a certain point. What direction does the magnetic field at that? What is the direction of the magnetic field? It's west, because the north, it's a compass, right? Let's see, I'm not gonna draw a full compass here, but let's see this is the compass. The south of the compass points east. And we know when we're using a plotting compass, we use the north. Wherever the north is pointing, that's where the direction of the field is. So the north is pointing this way. And what's the opposite of east? It's west. East. Select the diagram. Okay. Guys, I know these two look the same, but you need to focus. Obviously, north and south, the fields, they're gonna attract north and south. I don't know why here they're attacking. Here it's going, so it's one of these two. Here, it's going from the south towards the north, and we know that's wrong. It goes from north to south. Here it's going from north to south. That's correct. So that's let me zoom in a little. At any point on the magnetic field line, there can be one resultant force. That's why they don't cross. One resultant force only. All right.